All right, bonjour. Ça va? Comment ça va? Aujourd'hui, je veux teach you how to parler en ribosome. We want to learn how to speak ribosome. And ribosomes, what language do they use? Well, they use the language of DNA. DNA. So today our goal is to learn how the ribosomal language of DNA works. How do ribosomes read DNA? That's our task for today, mes amis. Let's go. Allons-y. All right. Hey now. Mr. Kovacs class. It's Mr. Kovacs class. You might learn a ton. It's Mr. Kovacs class.
He's interesting too.
It's Mr. Kovacs class.
And he's super cool.
It's Mr. Kovacs class. All right, let's review the basics. Remember, ribosomes make proteins, and they know how to make proteins because they can read the directions which are written in DNA. All right, first rule, of course, is there are only 4 letters in the DNA alphabet. T, G, C, and A. 4 letters. They stand for thymine, guanine, cytosine, and adenine. But you don't need to know their names. You just need to know their letters. In the 10th grade, you can worry about their names. Right now, like in the English language, you can make words out of letters by putting them together in certain ways. But in English, there are rules, right? Like you need to have consonants and vowels and all this stuff. In DNA language, the only rule is to make a word, you have to put 3 letters together. That's it. So C-A-T, that would work as an English word, cat, right? Meow.
Meow.
Meow. But it also works as a DNA word. Why? Because it's got 3 letters. It means something different. CAT means methionine. It's an amino acid.
Meow. What? Meow?
So if you were a ribosome and you saw CAT, you'd go, oh, methionine. You would not go, meow. In DNA, GGC is a word, right? That would not work in English, right? But in DNA, GGC is a word. That has meaning too. In DNA, GGC does not mean gugh. It means alanine. CAG, in English, CAG is a nonsense word. It doesn't mean anything. But in DNA, CAG means leucine. See, they all have meanings. They mean amino acids. And then in DNA language, to make meaning out of it, you string the words together. We call that in English a sentence. But in DNA, it's just a bunch of 3-letter words. And it tells the ribosome what amino acids to stick next to each other to make a protein. All right, so here are the rules of the language kind of written down, all right? DNA is the language of life. All living things, quote unquote, speak. Really, they don't speak DNA, you just read it. It's a written language. In English, you have letters, words, and sentences. In DNA, the equivalents are nitrogen nucleotide bases, codons, and genes. Letters, words, sentences, bases, codons, and genes. In DNA, there are only 4 letters in the alphabet. In DNA, words are called codons, and they can only be 3 letters long. Sentences, which are genes, can be thousands and thousands of codons or words long. There's no actual punctuation in the DNA alphabet, but there is a codon that tells you to stop reading. We call that a stop codon. Okay? So ribosomes get a copy of a gene, it's called messenger RNA, from the nucleus, and they follow the directions. Each gene just tells a ribosome how to make proteins. Each word in the sentence, each codon in the gene tells the ribosome which amino acid gets used next. And they string the amino acids together to make a protein. Human cells have about 30,000 genes in each cell. That means each cell you have could make about 30,000 different proteins. But I will promise you this, each cell in reality only makes about 2,000 proteins. They only make the ones they need to make. Your toenail cells do not make pepsin. That's the job of your stomach cells. All right, so let's see if we can apply this, okay? You should find attached to this part one, this piece of paper, right? This piece of paper is my secret code, right? So in the middle, there's really like two columns here. The letters of the DNA alphabet, the different codons, the different words. And then on the left-hand column, that's the amino acid. That's what it means in real life. For our purposes here, I am going to replace the amino acid with an English letter. And you'll see how that makes sense as we go here, right? So you've got 1, 2, 3, 5. There are only 20 some odd amino acids out there, and there are 26 letters in the alphabet, okay? And if you look at the first three, TTA, CTA, and TCA, those are all stop codons. That means if you're a ribosome and you read one of those, you stop.
Stop!
It doesn't matter if there's anything else coming after it, you stop.
Stop!
Ribosomes just stop when they get to stop codon. Stop.
Stop!
Stop. All right? So let's see, bust out your handy dandy little, we'll bust out the handy dandy little sheet here. All right? So my first piece of DNA here, TTC, AGC, TGT, TTA. We always read from left to right. So the first codon is TTC. We've got to find that here. Like if you're a ribosome, you'd have this memorized. But TTC, there it is, TTC. That's glutamic acid. So if you're a ribosome, you'd take glutamic acid and start the protein with that. In our little model here, we're not going to use glutamic acid. We're just going to write the letter C. All right, so I did a little worksheet here. You may find it helpful to do this. The first codon equals C. All right, let's see. Our second codon, AGC. Same kind of thing. We got to go look on here. AGC is alanine in real life, but today we're just going to use the English letter A. All right, so the first codon is C, second codon is A, third codon, let's see, TGT, TGT. We've got to look that up here. Again, if we were ribosomes, we'd have it. There's TGT, threonine, and we're going to use the English letter T. So we've got C, A, T, and then TTA is the stop codon.
Stop!
So our first gene, right, which was, TTC, AGC, TGT, TA, when we translate that into something that means something to us in English, we get meow.
Meow.
Meow. The cat protein. All right? So here's what you're going to do. I'm going to give you the next gene. You'll hit pause, and then you'll decode it, and then I'll ask you to tell me what the decoded version was. All right? So this is next. This is GCC, ATC, AAT, CTA. I'll say that again. GCC, ATC, AAT, CTA. I want you to decode that gene. Good. We made cat before, now we made dog. Woof, woof. All right, we'll try it. We're not gonna do too many. Oh, I got a little bit longer. TGT, ATC, TCGGG, AGC, ATTC, ATCTA. TGT, ATC, TCGGG, AGC, ATTC, ATCTA. Can you decode that now? Good. That was toenail. You made a toenail. All right. So let's see. If you're a ribosome, we'll just do this quickly. If you got this piece of DNA, you would click say like, oh, that means fast. F-A-S-T, fast, stop, right? Here's what's weird about DNA and why they take so much time copying it correctly. See this right here, this letter G? If you copied it but used the wrong letter, that could totally change the meaning, right? I mean, think about it, okay? If you copied this wrong, GTG, AGD, and instead you put a C where that G should have been, you may get a totally different meaning. Can you imagine what the cell would be like if it wanted to go fast? But if the ribosome read it this way, that's not a cell you want to be in. That's a malfunctioning cell because of we call this a mutation. All right? So by now, hopefully you've decoded a few genes. If you change one letter in a gene, that's called a mutation, and that can have huge, huge implications on what happens to the cell. We call the copying of a gene in the nucleus to make messenger RNA is called transcription. And then what you just did was you translated like a ribosome. Translated. You made a protein. All right? Don't worry, we're going to practice this some more and you'll become an expert at speaking DNA. Maybe I'll have you write all of your next assignments in DNA. No, probably not.